You know, sometimes when I think about things in my head, and I say, you know, I just saw light coming through that screen door. And look at the meringue effects that are happening on the ground. Can I go draw that? No way. But I can describe that to my mathematician. This kind of reminds me of... He sends me back the generator, all ready for me to try. And I sit down at the computer and say, well, let's see what it's doing. And I have parameters that I can control. And I keep pushing, and I go, wow, this is not what I expected at all. At all, but it's cool.
Use the Force, Luke.
The same kinds of fractal design principles have completely transformed the magic of special effects.
This is a key moment from Star Wars Episode 3, where our two heroes have run out onto the end of this giant mechanical arm, and the lava splashes down onto the arm. My starting point here is to actually take the three-dimensional model and take essentially a jet and just shoot lava up into the air. This looks kind of boring. It's doing roughly the right thing, but the motion has no kind of visual interest to it. Let's look at what happens here when I add the fractal swirl to it. Where this becomes fractal is, we take that same swirl pattern, we shrink it down and reapply it. We take that, we shrink it down again, we reapply it. We shrink it down again, we reapply it. And from here on, it's just a case of layering up more and more and more. I've used the same technique to create these additional lava streams. I then do it again here to get some just red hot embers. Then we take all of those layers and we add them up and we get the final composite image. My hero lava in the foreground, the extra lava in the background, the embers, sparks, steam, smoke.
Designers and artists the world over have embraced the visual potential of fractals. But when the Mandelbrot set was first published, mathematicians, for the most part, reacted with scorn.
In the Mathematical Intelligencer, which is a gossip sheet for professional mathematicians, there were article after article saying he wasn't a mathematician, he was a bad mathematician, it's not mathematics, fractal geometry is worthless.
The eye had been banished out of science. The eye had been excommunicated.
His colleagues, especially the really good ones, pure mathematicians that he respected, they turned against him.
Because, you know, you get used to the world that you've created and that you live in, and mathematicians had become very used to this world of smooth curves that they could do things with.
They were clinging to the old paradigm when Mandelbrot and a few people were way out there bringing in the new paradigm. And he used to call me up on the telephone late at night because he was bothered and we'd talk about it. Mandelbrot was saying, this is a branch of geometry just like Euclid. So that offended them. They said, no, this is an artifact of your stupid computing machine.
I know very well that there is this line that fractals are pretty pictures but are pretty useless. Well, it's a pretty jingle, but it's completely ridiculous.
Mandelbrot replied to his critics with his new book, The Fractal Geometry of Nature. It was filled with examples of how his ideas could be useful to science. Mandelbrot argued that with fractals, he could precisely measure natural shapes and make calculations that could be applied to all kinds of formations, from the drainage patterns of rivers to the movements of clouds.
So this domain of growing living systems, which I, along with most other mathematicians, had always regarded as pretty well off limits for mathematics and certainly off limits for geometry, suddenly was center stage. It was Mandelbrot's book that convinced us that this wasn't just artwork. This was new science in the making. This was a completely new way of looking at the world in which we live that allowed us not just to look at it, not just to measure it, but to do mathematics and thereby understand it in a deeper way than we had before.
As someone who's been working with fractals for 20 years, I'm not going to tell you fractals are cool. I'm going to tell you fractals are useful. And that's what's important to me.
In the 1990s, a Boston radio astronomer named Nathan Cohen used fractal mathematics to make a technological breakthrough in electronic communication. Cohen had a hobby. He was a ham radio operator, but his landlord had a rule against rigging antennas on the building.
I was at an astronomy conference in Hungary, and Dr. Mandelbrot was giving a talk about the large-scale structure of the universe and reporting how using fractals was a very good way of understanding that kind of structure, which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helga von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable in my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well. And I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was, frankly, an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals, experimentally, I came up with a very wideband antenna, and then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have self-similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas sticking out at the same time. The alternative option is you can let your cell phone look like a porcupine, but most people don't want to carry around a porcupine.
Today, fractal antennas are used in tens of millions of cell phones and other wireless communication devices all over the world.
We're going to see over the next 10 to 15 to 20 years that you're going to have to use fractals because it's the only way to get cheaper cost and smaller size for all the complex telecommunication needs we're having.
Once you realize that a shrewd engineer would use fractals in many, many contexts, you better understand why nature, which is shrewder, uses them in its ways.
They're all over in biology. They're solutions that natural selection has come up with over and over and over and over.